So in this section, we're going to investigate powers raised, or expressions raised to the zero power, and then expressions that have negative exponents. So first we're going to talk about the zero power by first establishing a pattern and then proving why that pattern works. So 2 to the 5th would mean to do 2 times 2 times 2 times 2 times 2, which would be 32. 2 to the 4th, 2 times itself 4 times would be 16. 2 to the 3rd would be 8, 2 to the 2nd would be 4, and 2 to the 1st would be 2. So over here you can see that the pattern is decreasing by 1 every time. So over here the pattern you can see is dividing by 2. 32 divided by 2 is 16, divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. So if we divide by 2 again, it would make sense that we're going to get 1. So now we're going to come over here, and the first thing that we're going to use is the idea that 5 times 1 is 5, and 4 times 1 is 4, and 3 times 1 is 3, or b times 1 is b, which is really that anything times 1 is itself. So we're going to use this fact, and that's something that I feel like everyone knows, that anything times 1 is itself. And we already know that if you're multiplying expressions that have the same base, then you're allowed to add their exponents. We proved that back in section 8.1, that x to the m times x to the n would be x to the m plus n. And so we know that, and we also know that anything times 1 is itself. So if I want to multiply x to the 3rd by something and get x to the 3rd, it would make sense that I would have to multiply x to the 3rd by 1, because x to the 3rd times 1 would be itself, which is x to the 3rd. Now if I use exponents and multiply x to the 3rd by x to the something, this rule tells me that I'm going to add the exponents, which are the 3 and the question mark. So if I want to add the 3 and the question mark and end up with a 3, then the only number that that could be is 0, because 3 plus 0 is 3. So then that means x to the 0 had to be 1. These two things had to be equal. So anything to the 0 power is going to be 1. So for my first rule, I'm just going to write that. A to the 0 power is 1. And the only thing that a actually can't be is 0. You just can't have 0 to the 0 power. It's like you're not doing anything. Doing a calculator to get error. So a can be positive, a can be negative, a can be a fraction, a can be a decimal. A just can't be 0. Anything to the 0 power is 1. So just to get some basic practice with that, here I have 2/3 to the 0 power. It doesn't matter that it's a fraction. The answer is 1. And then on the next one I have -1 to the 0 power. It doesn't matter that it's negative. The answer is 1. And again, anything to the 0 power is 1. So the next thing we're going to investigate is negative exponents, and we'll do it a similar way. We'll first establish a pattern, and we'll kind of prove it mathematically. So 2 to the 3rd means 2 times 2 times 2, which is 8. 2 to the 2nd means 2 times 2, which is 4. 2 to the 1st is 2. 2 to the 0 we just learned is 1. So if you're looking at your exponents, again, you're decreasing. So it would make sense to go 3, 2, 1, 0, and then -1, -2. And on this side, we're still dividing by 2 every time. So 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So the next one would be 1 divided by 2, which I would just actually write as 1 divided by 2. Now if I want to write that as a power, I could write that over as 1 over 2 to the 1st power, because 2 to the 1st is 2, so 1 over 2 to the 1st would be the same as 1 over 2. So now if I divide by 2 again, because remember that's my pattern here, is divide by 2, so if I just do that for a second, 1/2 divided by 2, that would really mean to do 1/2 times the reciprocal, which is 1/2. That will come out to 1/4. So 2 to the -2 is really 1/4. But as a power, that would be 1 over 2 to the 2nd, because 2 to the 2nd is 4. So what you can see is that here, it was 2 to the -1st. The negative exponent became positive when it became a fraction. And here, the negative exponent became positive when it became a fraction. So now, if I look over on this side, I already know this rule. We proved this in 8.2. Where as long as your bases are the same, which they are, they're both A, and you're dividing, which we are, then you're allowed to subtract the exponents. So according to that rule, if I apply this rule here, 2 to the 4th divided by 2 to the 5th would mean to do 2 to the 4 minus 5, which would be 2 to the negative first. But let's see what happens when we expand it. So on the top, I'm going to have 2 to the 4th, which would mean 2 times 2 times 2 times 2. And on the bottom, I have 2 to the 5th, which would mean 2 times 2 times 2 times 2. One missing, there it is, times 2. And so then if I do my canceling, just like I did before, these 2's would cancel, these 2's would cancel, these 2's would cancel, these 2's would cancel. Remember, every time they're really canceling, they're making a 1. So my numerator is a 1 because there's nothing left on top, so it's a 1. And on the bottom, I'm left with 1, 2. So if I apply the subtraction shortcut, I get 2 to the negative first. But if I expand, I get 1 over 2. So that means that these must be the same. And so what I'm going to do for this section is I'm going to write my answer always with a positive exponent. So writing an answer with a negative exponent would be similar to not, say, reducing a fraction. Like you would never leave an answer as 2/4. Same kind of an idea. You wouldn't leave an answer as 2 to the negative 1 because a negative exponent means that it's not simplified. So the math behind this is going to be if you have a to the negative m, you're going to make it 1 over a to the m. So what's going to happen is this is going to become a fraction, and in doing that, that's what's going to turn your power positive. So on this first example, x is being raised to a negative power, and so what we just learned is that the way to make it positive power is you make it a fraction. 1 becomes your numerator as you're cutting a placeholder. X would move to the bottom, and in doing that, the power becomes positive. So this would become 1 over x squared. On the next example, 4 is your base. It's being raised to a negative power, so that's not in simplest form. The way that I make the power positive is I make it a fraction with a 1 as my numerator. 4 moves to the bottom, and its power becomes positive. Now, because I'm simplifying, I'm actually going to do that out. So on the bottom, I have to do 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. So my final answer is actually going to be 1 over 64. And then on this last example, my base is negative 8, and it has a negative exponent, so the way that I make it positive is I make it a fraction. I'm going to move the base to the bottom, which I'm going to keep in parentheses, and then my power becomes positive. And so now I'm going to square negative 8, which means to do negative 8 times itself, which would be positive 64, so 1 over 64. Another way that I think about negative exponents is I almost think about them like the game Whack-A-Mole. So where, you know, the mole pops up and you whack it with the mallet. So if you see something with a negative exponent, so like in this case, x has a negative exponent, 4 has a negative exponent, and negative 8 has a negative exponent. So what you're looking for is you're looking for negative exponents. And if you see one, you whack the base. And so when you whack the base, just like the mole goes back in the hole, the base would go to the bottom of the fraction, and then its exponent becomes positive. Not a very mathematical way to look at it, but just kind of one way to think about it. So scan through a problem, look for negative exponents, and if you see them, hit the base that has a negative exponent. It will go to the bottom of your fraction, and then its exponent will become positive. So these two examples are a little bit different because the denominator already has a negative exponent. So I'm actually going to rewrite the first one using two different colors. So I'm just going to rewrite it as 1 over y to the negative third. So the part that has a negative exponent is y to the negative third. The numerator is fine, so I'm going to keep my numerator, make it equal. And then I just learned that in order to simplify this, the y would move to the denominator of another fraction, and its exponent would become positive. So if you can kind of ignore this for a second, I'll even cover it with a rectangle. So if all you had ever seen was y to the negative third, we had just learned that that would become 1 over y to the third. But during this problem, this 1 was on top the whole time. So then if I kind of reveal, then it's there. So now, if I read this out loud, what this is saying is 1 divided by 1 over y to the third. So I could write that as 1 divided by 1 over y to the third. So I'm dividing a number by a fraction. And the way that I divide fractions is I actually multiply by the reciprocal. And the reciprocal of 1 over y to the third is just y to the third. And so then I'd end up with y to the third as my answer, because y to the third times 1 would be y to the third. So if you look at the answer for a second, and then back at the original, y started at the denominator, and it ended up in the numerator. And that's how the exponent became positive. So if something's already in the denominator with a negative exponent, you're going to move it to the top. And moving it to the top is what will make the exponent positive. If something's in the numerator, you move it to the denominator, and that's how you make the exponent positive. So on this second example over here, 2 is already in the denominator. So to make it a positive exponent, I would move it up to the top of the fraction. And by doing that, its exponent would become positive. Now in the bottom, there's technically still a 1. It could be over 1, but you really don't even need that because it's over 1. And then I would simplify that further. 2 to the third is 8, because 2 times 2 times 2 is 8. So if you apply kind of the whack-a-mole concept, this would be an example in the game where you accidentally hit a mole that's never popped up. So he kind of bounces off the floor and goes to the top, and that becomes a positive exponent. So just to add to this second rule, where if you have a to the negative m, that becomes 1 over. So just if you already had 1 over a to the negative m, so the case where you have a negative exponent but it's already on the bottom, it's going to become a to the m. So on the next 2 slides, we're going to kind of put everything together. So do a couple of examples together, and then I'll have you do it on your own. So on this first example, there's 2 ways to do it. Because you have 7 to the third divided by 7 to the fifth, you could apply the subtraction shortcut, which would mean to do 7 to the 3 minus 5. But then 3 minus 5 is negative 2. And so now if you think of this as a fraction, it's not, but if you think of it as a fraction, it's over 1. So 7's in the numerator. You would move the 7 to the denominator, so it would become 1 over. And by doing that, your exponent would become positive. And then 7 times 7 is 49. So 1 over 49. That's kind of one way to think about this problem. A good way to check it is to just visualize your 7's. So 7 to the third means you have 3 7's on top. 7 to the fifth means you have 5 7's on bottom. So after you do your canceling, you're going to have 2 leftover 7's. And the 2 leftover 7's are going to be on the bottom because there were more 7's in the denominator to begin with. So that's just a good way to check your answer. On this next example, I need to get rid of the parentheses first. And the way that I'm going to do that is I'm going to raise everything to the third power. So there's 3 items, if you think about it, inside the parentheses. The first item is your 2, the second item is your x, and your third item is y to the negative fifth. So I want to raise each of those to the third power. So first I would do 2 to the third power, x to the third power, and then I would do y to the negative fifth to the third power. But we learned in the last or an earlier section that when you're doing power to a power, you multiply the exponents. So now if I look at my 3 bases, 2 has a positive exponent, so he won't move. X also has a positive exponent, so he won't move. But y does have a negative exponent. So what's going to happen is the 2 and the x are going to stay where they are in your fraction, which is on the top. And I'm actually going to simplify them. So 2 to the third means 2 times 2 times 2, and that's 8. x to the third is just x to the third. Now because y has a negative exponent, it's going to go to the bottom. So it's going to become y, and by moving y down, that's what's going to change the exponent to positive. So your final answer on that problem would be 8x to the third, y to the 15th. If you think about whack-a-mole, you're not going to whack the 2 because his exponent's already positive. You're not going to whack the x, his exponent's already positive, but the y gets whacked down because his exponent's negative. So you're going to pause the video, try the next two examples, press play when you're ready to check your answer. Make sure you're simplifying as much as you can, and your final answer should only contain positive exponents, no negatives. So for the first example, we're going to get rid of the parentheses by raising each item inside to the third power. So that means to do 3 to the third power, x to the negative 2 to the third power, but because it's a power to a power you can multiply, so that becomes x to the negative 6th, and then y to the second to the third power, and again you can multiply, so that becomes y to the 6th. So of my 3 items, only the x has a negative exponent, so that's the only one that needs to move. The other 2 will stay. So 3 to the third, 3 times 3 times 3 is 27, and then y to the 6th, those stay on the top, they don't go anywhere, but x gets bumped to the bottom because that's how you make the exponent positive. So your final answer is 27 y to the 6th over x to the 6th. This one, there's actually 2 ways to do it, so here's just one of the ways. Because the 5s are dividing each other in the same base, the shortcut says you could subtract the exponents, so you could do negative 1 minus 2. But negative 1 minus 2 is negative 3, and so then 5 would get bumped to the bottom, which would make it 1 over 5 to the third, and 5 to the third is 125. Another way to consider this is if you look at your 5s, you're only going to move a base if its exponent is negative. So the 5 that's on the bottom is going to stay where it is because it has a positive exponent. The 5 that's on the top has a negative exponent, so he's going to get bumped down. So when I bump him down, the exponent becomes positive, and my placeholder on the top is a 1. So now on the bottom, because I'm multiplying the 5s, which have the same base, I'd be allowed to add the exponents. So I'd get 1 over 5 to the third, but then 5 to the third would get me 1 over 125. So either the blue way or the green way is totally fine to do that problem. On this next example, I want to start by getting rid of the parentheses. And to do that, I'm going to raise everything inside to the negative 2 power. Now I can't actually do an exponent until it's positive, so I don't know what 2 to the negative 2 would be. I just know that this 2 is receiving the power of the negative 2. And then same thing on the bottom, I have a 3 that's receiving the power negative 2. Can't do the math until the exponents are positive because I don't know a mathematical way to do negative exponents. So because 2 has a negative exponent, this 2 is going to get bumped down. So now 2 would be at the bottom, and that would make its exponent positive. 3 is already at the bottom, but it has a negative exponent, so to make the exponent of 3 positive, I'm going to move it to the top, which would make the exponent positive. Now that the exponents are all positive, I can actually do this. 3 to the second means to do 3 times 3, which is 9. 2 to the second means to do 2 times 2, which is 4. So my final answer on that problem would be 9 over 4. Pause the video and do the next 2 examples. Press play when you're ready to check your answer. Make sure everything is as simplified as it can be, and all your exponents are positive when you're done. Okay, so on this first example, I want to start by getting rid of the parentheses. And the way that I do that is I give this power, or raise everything in the parentheses, to the negative 2 power. So 2 is being raised to the negative 2 power, which I can't do until it becomes positive. X is also being raised to the negative 2 power. Everything else I just rewrote. So then I looked through the entire problem to see of all of the items, which ones had negative exponents. Because if something had a negative exponent, I wanted to make the exponents positive by moving them either from top to bottom or bottom to top. So 2 has a negative exponent, so I moved him down, which made the exponent positive. X also had a negative exponent, so I moved him down, which made the exponent positive. Y to the 5th doesn't move, his exponent's already positive. Y to the second, x to the second don't move. And while 4 is negative, its exponent make sure, is actually positive 1. So even though the 4 is negative, it doesn't move. It stays where it is because it has a positive exponent. So now that I have all my exponents positive, I can start to simplify. So y to the 5th divided by y to the 2nd. The shortcut tells me that because the bases are both y, I'm allowed to subtract the exponents, which would leave me with y to the 3rd. And if you think about it, the reason it's on the top, this means 5 y's on top, 2 y's on bottom. There'd be 3 more y's, and they'd be located on the top because there's more y's on top. X to the 2nd times x to the 2nd. Remember, when you're multiplying, the shortcut tells you can add. That would be x to the 4th. And then the negative 16 part comes from 2 squared, which is 2 times 2 is 4. But then 4 times negative 4 would be negative 16. So a final answer of y to the 3rd over negative 16 x to the 4th. On the next example, there weren't any parentheses, so I didn't have to worry about that. So I just look at each item, 4x, y, 8x, y, and I'm looking for negative exponents, because if something has a negative exponent, I'm going to move it. So the only thing with a negative exponent was this x. So that x got moved to the bottom, and by moving it to the bottom, its exponent became positive. Everything else stayed where it was. 4 stayed, y to the 4th stayed, 8x, y to the 6th, they all stayed where they were. X to the negative 2 went to the bottom. The next thing that I noticed is that I had a 4 and an 8. And so if you ignore the rest, everything else, all the x's and y's, and you just picture a 4 over 8, you would never leave it like that. You would reduce it by dividing by 4, and you get 1/2. So that's where the 1 and the 2 came from. I divided both 8 and 4 by 4. Then I also look to simplify everything else. So x to the 2nd times x, which there would really be 2 x's, and a third x would be x to the 3rd, or you could add an exponent of 1. And then y to the 4th, so that means you have 4 y's on the top. Y to the 6th, you have 6 y's on the bottom. So after you expand all your y's and do all your canceling, you'd have 2 y's left, and those leftover y's would be on the bottom, because there were more y's in the bottom. There were 6 on the bottom and only 4 on the top. So if you can visualize your y's, that's one way to do it. You also could have applied your subtraction rule, which says because the y's are dividing each other, then you can subtract their exponents. And so then y to the 4 minus 6 would be y to the negative 2, but the fact that its exponent is negative means it ends up in the bottom. It's really helpful to visualize when you're doing these kinds of problems, especially with negative exponents. How many are on the top? How many are on the bottom? After you cancel, how many are left, which in this case was 2. And where are those leftovers? And in this case, because there were more y's on the bottom, 6 versus 4, the leftovers would be on the bottom.